Absorption spectra. What the hell is that? Hi, I'm your host with the most, Tylor Mariano, and welcome back to Physics 101, where 3 contestants today will be wanting to earn hard-earned cash. Alright, so now let's meet our 3 contestants.
I'm Evan Yamamoto. I'm 16 years old, and if the sun were made out of bananas, it would be just as hot.
So now let's meet contestant number 2.
My name's Ginoza, and I'm 16. And the faster you move, the heavier you get, and I'm pretty fast.
And now let's meet contestant number 3.
Hi, I'm Jarron. I'm 16, and the universe is rapidly expanding, just like my belly.
So our theme today is Chapter 7, and it's about discrete energy and radioactivity. Okay, so question 1. What is the equation for the energy of a photon?
Go.
E equals HF.
That's correct. Can you please elaborate on why that answer is correct?
In the equation E equals hf, E is equal to the energy of the photon, which is measured in joules, h is the Planck's constant, and f is the frequency of light.
Question 2. What is another equation of energy of a photon?
The equation is E equals hc divided by lambda.
That is also correct. Can you please explain why?
In the equation, E equals hc divided by lambda, E equals the energy of photons, which are joules, h equals Planck's constant, which is 6.63 times 10 to the negative 34 joules per second, c is the speed of light, which is 3 times 10 to the 8th meters per second, and lambda is the wavelength of light.
Question 3. Calculate the wavelength of the photon emitted in a transition from n equals 4 to n equals 2 in hydrogen.
This is one of the energy level diagrams for hydrogen and mercury, respectively, according to Bohr's calculations. The right side is measured in electron volts, and the left side is the energy level, represented by N. The ground state, which is at the bottom of the energy level diagram, is the state of lowest energy. Okay, so looking at the energy level diagram for hydrogen, you have at N equals 4, negative 0.85 electron volts, and at N equals 2, we have negative 3.40 electron volts. So, and in order for this problem, we have to find the difference between those two, and for that we're going to subtract negative 0.85 by negative 3.40, and from that we get 2.55 electron volts. And in order to solve the rest of the problem, you have to convert electron volts into joules. So in order to do that, you have to convert it, and the conversion between those two is 1.6 times 10 to the negative 19th, and after you multiply that out in your calculator, you get 4.08 times 10 to the negative 19th. And the equation that we're using to solve this problem is E equals hc over lambda, but since we need the wavelength, we solve for lambda and we get lambda equals hc over E. So now plugging in variables, h, which is Planck's constant, that is 6.63 times 10 to the negative 34th, and that's going to be multiplied by c, which is the speed of light, and that is 3.0 times 10 to the 8th, and for E, which we already solved for up here, that is 4.08 times 10 to the negative 19th. After plugging that into your calculator, the wavelength that we are going to get is 4.88 times 10 to the negative 19th meters, but since we're working with sig figs, you round it to 4.9 times 10 to the negative 19th meters.
And the winner is nobody, because you all tied with 1 point. And the prize was nothing. You all get nothing.
This is boring.
Oh look, a channel on discrete energy.
Hello, my name is Professor Ginoza, coming to you from the Manila State University in the Philippines. Today I'll be lecturing about discrete energy and the energy level diagram. First, looking at the diagram according to Bohr's calculations, each horizontal line represents a possible energy of the atom. This means the kinetic energy of the electrons and the electric potential energy of the electrons and the nucleus. There are certain values on the left side of the diagram which represent the energy in electron volts. No other values are possible. This means that the energy is discrete, which also means it can only have one out of a specific set of values rather than being continuous. Bohr said that atoms can transition from a higher energy state to a lower energy state by giving off a photon, which is also a particle of light. Each photon can be thought of as a tiny flash of light. With lots of transitions, these tiny flashes in each transition in total become the observable or visible light we see in the emission spectrum. When they are disturbed, the electrons in each atom will be at the lowest energy state, or at n equals 1. This is the ground state. When energy is added, the electron may move to a higher level, or an excited state. But immediately once it reaches the excited state, the electron will make a transition down to one of the available lower energy states. When an electron in an atom falls from a higher energy level to a lower energy level, it emits a photon to carry off the extra energy. This photon's energy is equal to the energy difference between the two energy levels. This is called relaxation. For example, from n equals 3, it can drop off straight to n equals 1, or it can drop from n equals 2 and then to n equals 1. Salamat po.
Hello, I'm the assistant to Professor Ginoza. My name is Abundio Bautista, and I'll be talking about emission spectrum versus absorption spectrum. The dark lines correspond to the frequencies of light that have been absorbed by the gas. As the photons of light are absorbed by electrons, the electrons move into higher energy levels. This is the opposite process of emission. The dark lines, absorption lines, correspond to the frequencies of the emission spectrum of the same element. The amount of energy absorbed by this electron to move into a higher level is the same as the amount of energy released when returning to the original energy level. Okay, now I understand.